All right. Having fun over here this morning trying to get everything running on time. This is a lot easier when you just got to walk from class to class. Surprisingly. All right. So as a reminder, 4.4 is due on the 8th for my Math Lab homework. 5.1 is going to be due on the 15th. We had said I gave you a small little extension on that due to the midterm. Our project is due today. Today. I will not give any extensions on this project. You have had more than enough time with this. I know that some of it was during our extended spring break, but that didn't mean you couldn't have been working on it then. So if you are one of those people who loves to wait to the last second to do things, you're going to have fun today. Some of you have been emailing me asking questions about this, and those of you who have know that my answers are typically pretty open-ended. I'm not going to tell you exactly what to do. That's the point of a project. You are supposed to have gained enough knowledge from doing Excel homework to be able to do all of this stuff. You've got to make sure you know what your rows and columns are. Remember, there's two parts of this project, and the second part should be very, very easy. It is way shorter than the first part. Do not overcomplicate that second part, and don't skip it because it's 40 points. You're just prorating things. We've explained what prorating means. If you've forgotten, go back to your notes or go to the internet, and Google will probably help you. And remember that we're prorating to monthly. Make sure you're going to Canvas to where it says submit project here, and you're actually submitting it there. If you email me your project, I'm not grading it. If you somehow find another place to put it, if you submit it somewhere in my math lab, I'm not grading that because I don't even know where you're putting it. If you go to your grades in Canvas, you may notice that there's a second project column. It's like called Project 1. I have been trying to delete that all semester and I can't get rid of it. Well, I'm not going to act like I've tried to do it for hours or something, but I've tried a couple times. And I didn't figure out why I couldn't delete it. And it's not really a problem because you don't see it on the main page, just the grade book, and it's blank, so don't worry about that. Your next Excel file to be done is that lines due on the 15th, which is a week from today. Remember that your midterm review is available in Canvas. It's like 55 to 60 questions. I told you to skip one of them, or at least part of one of them, so please make sure you pay attention to the instructions literally in the file link. The midterm will be available in my math lab starting on, oh, what's that? Today. And then it's due on the 13th by midnight. So I believe I have that available. I want to confirm that real quick. If you go into assignments, look at that. Midterm, chapters 1 through 4. You get 2 attempts, time limit of 2 hours, and it's due on the 13th by midnight. Please don't wait till the 13th to do your first attempt. Please don't wait till the 13th to start studying for this test. Just start looking at the review. Please don't ignore the review. These are critical things to start working on now while the material is fresh, to give you some extra time. If you do your first attempt maybe in a day or two and you don't do well, that'll give you some time to know what you need to study to then do well the second time. Again, I'm not really going to be giving partial credit for this stuff. It would be a very, very, very rare circumstance that I do give partial credit, and that's pretty much true for all my classes. You have to complete that in one sitting. I take your best grade only. Complete it on your own. I did provide a formula sheet that's in Canvas as well. Let's see. I don't want to pull that up because you might see something. Okay. All right. So let's pull up our notes, and we're in 5.2, Slopes and Y-Intercept. And we gave the slope formula last time. We gave you slope-intercept form last time. So if something's solved for Y, we said that the constant is the Y-intercept, and then that can be very often, but not necessarily, translated as or interpreted as the starting value or initial value. But not always. When we get into applications, when we're given real life data points, a lot of the times, as we'll see, the starting values don't necessarily make sense. And then we did some worksheet examples where we interpreted the slope given the equation and given a graph. And those were on pages like 200 and 201, and I think we only did A and B. Yes, in fact, we only did A and B. So we're going to pick up with number 3 on page 201 of your worksheets, and then we're going to go straight into the next section of the worksheet as well. All right, where was that? Here we go. So this was the last one we did, that concentration of pollution, and we interpreted that as the concentration is changing by negative 0.8 parts per million per day. And remember, we had this right here. The output is changing by the slope and then the Y units per X units. So the output is the thing we're discussing. What are we interested in? So for number 1, it was the cost. So the cost is changing by. Then you write the number for the slope in the units of the Y values, the outputs. Costs are in dollars. And then you say per and whatever the X units are. There's no number for the X because we're always assuming it's a 1. We're doing it per 1. We're scaling it to 1, something that we've done in this class before, but we don't actually have to do any math. It's already scaled to 1 because these are written as decimals or whole numbers, never fractions for us. So again, and I don't think I can copy paste, so we'll just have to leave that there. The output is changing by slope, Y units per X units. So up to number 3, really wish I could edit this. All right. First, I want to mention something about this number right here. This 5e plus 0.6. This is a number that's in scientific notation. We've seen this in class at least once before, but 5e plus 0.6, what that tells you is that there's a decimal after the 5 and you're going to move it right 6 times. So 1, 2, 3, 4, 5, 6, which is really 5 million. So this is really a 5 million right here. If that was a negative 0.6, then it would move left. So just as a note, 5e minus 0.6, that's saying that you need to move the decimal left 6 times. And when you move the decimal left 6 times, you're going to end up with 5 zeros in front of the 5. So that would be equal to 0.123455 of those zeros, and then a 5. Okay, not the point of the problem at all, but that's going to be relevant for when we get to the next section. So interpret the slope. Interpret the slope. Remember, it's y equals mx plus b, where the number in front of the x is the slope. So this number right here is the slope. I don't even need this number at all for this problem. I don't even care what it is. Now, I'm not saying I don't care what it is in general, I just don't need it for this particular problem. So the slope is the 123,139, but we got to make that statement from before. So it's the output, I'll write this one last time, is changing by, and remember I said you can substitute the phrases is increasing or decreasing depending on positive or negative, by, and then you write the slope, and I'll stick with those little sideways V's for their notation, and then it goes y units per x units. So we talk about all the y stuff, then the x stuff. So for this one we say, what's the output? Growth in Houston metro area. Growth in Houston metro area. Well, this is talking about people, so I guess it's population. So the Houston metro area population is changing by, since the slope's positive, we could also say instead is increasing by. Then we write the number for the slope, which is 123,139. Then we write the units that the y is in, which is people, the output. Then the word per, and then the type of X unit, which is years since 2000. I can't just say year. If I say year, this is wrong because this model is not talking about every single year. If I just say per year, then I'm okay, well, in the year negative 30 million in terms of AD, so 30 million BC, if you will. That huge Houston metro area population was definitely not changing by 123,139 people per year in the year 30 million BC, because Houston didn't even exist. So this year since 2000 is trying to narrow our window, what we're looking at. We're only talking about any year since 2000. When we talk about population dynamics, this aspect is insanely critical because population dynamics tend to change every 20 or 50 or 100 years, depending on what we're talking about. And that's something that you're going to hear me discuss a couple of times where I'll say, okay, you can model population linearly, this is a line, if you only want to look at, say, 10 or 20 years. But if you want to look at 100 years, you have to look at this as what is known as an exponential model, which means it's not a line, an exponential model, as we'll see in a later section. It starts out kind of flat, but then eventually it starts growing quicker and quicker and quicker. And again, I've related this to COVID right now. And then eventually, I'll mention this, but we never study it officially in here, but it's important to understand that logistical growth is what exponential tends to turn into in the long term for population dynamics. Because eventually we run out of room and resources, so things taper off and they flatten out. So this is the exponential section, which again is where we still are with this COVID-19 thing, but eventually we're gonna run out of room, i.e. people to infect, so it tapers off and kind of flattens out to some maximum number. So linear growth is good for short term. Exponential is good for mid, logistical is good for long when we're talking population. Okay, I gotta clear my screen so I can scroll down. Monthly interest. Interpret the slope, which means we're only interested in the number in front of the x. So this minus 2e minus 11, that's in scientific notation again. So I'll just make a little memo on that that is irrelevant for this problem. Ooh, that got all kinds of weird. 2e minus 11. That means you're taking the decimal and moving it 11 times to the left. It's originally after the 2, which will give us 10 of these zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the 2. That's a teeny number. It's pretty much 0. Okay, monthly interest. The monthly interest as a function of monthly balance for an annual percent rate of 6%. So we're seeing 6% growth, no matter what type of account this is, whether it's savings or a loan or whatever. So this line is only showing a very small segment of something. We're starting here at 16,400 roughly, maybe that's 500. And then the furthest point to the right we have is 18,000. And then the heights are ranging between 82 and what looks like about 90. This is an interesting graph because it does not start at 0. This x number here is not 0. This y number is not 0. And, well, that's interesting because if you redrew this graph, if you actually wanted to have the zeros there, I'm going to give myself some space. I said clear screen. You silly goose. There we go. That's too low, isn't it? There we go. So I'm just going to redraw this graph. I'm going to erase it afterwards. This is not part of the problem, but I want to show you what I'm talking about, how these aren't starting at zeros. So it's very easy to misinterpret this graph. The media would love this because, oh, okay, this doesn't look too bad. This is a lot higher, so this is terrible. But honestly, it's not that much of a difference between having an interest of $82 and $90. If you start everything at 0, oops, So this is in dollars. Let's just go in intervals of $1,000. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So here's our 18,000. I don't want to label every single one of those. And then the heights, we got to go up to about $90. So let's just go in intervals of 10. So 10, 20, 30, 40, 50, 60, 70, 80, 90. And again, not going to label everything. So these are in dollars. This is a balance. And this over here on the left was interest, because that says interest. So this point is about 16,500, which is roughly here, and then has a height of 82, which is about here. So that point is that point. Then this far right point is at 18,000 and has a height of 90, which is right here. That line is the same data represented, but now where everything starts at a zero balance, which would give you zero interest. APR is based on the balance of a loan, or the balance of how much you have in an account. So if you have $0, you're getting $0 in interest. If you have $1,000, you're going to get something. If you have 2,000, you're going to get twice as much. If you have 10,000, you'd get 10 times as much. So again, the media is probably going to love this graph because it doesn't really show you the rest of what's going on. So if I extended this graph, now if I was a perfect artist, wow, this is going to be actually pretty good. Come on, come on, come on, come on, come on. There we go. This would extend. I didn't represent any of this blue information, but it would be true because this slope would be constant throughout this. I don't want to take this past zero because we can't have a negative balance on a loan or a savings account, no matter what SunTrust tells us about our negative bank balance in our checking account because they took our money because we didn't have enough. That's a whole nother scenario. And you're not going to get negative money and interest. So again, this is really the same graph, but the red is only being illustrated here. So I'm gonna leave that up for about another 10 or 15 seconds, and then we'll actually start the problem. Okay, so let's clear our screen. Now let's interpret the slope, which is the number in front of the x if it's solved for y. That's our m, 0.005. So we can say the output. What's the output? Monthly interest. You don't want to just say interest because is it the yearly interest? Is it the daily interest? Is it the quarterly interest? Is it the total interest? No, it's the monthly interest. Then we go, is changing by. And then we write the slope, which is 0.005, and that was dollars. Now, I can write the dollar symbol in front of it or the word after it. And then this would be per. And then the input is based on the monthly balance. So per dollar of your monthly balance. Now, I know we normally don't write a number here, but we want it, if we just say per monthly balance, I don't feel like that is detailed enough. The monthly balance is based on dollars. So per dollar of monthly balance. You could also say that the monthly interest is changing by 0.5 cents per dollar of monthly balance. Or you could say, if you don't like the fact that none of these are whole values, you could scale instead of the per dollar, you could scale that to per 100. This is not something I'd have you do, but it's something they like us to mention. So you could say the monthly interest is changing by, and this would be $0.5 because you moved the decimal right twice. That would scale the dollars to $100. So by $0.5 per $100 of monthly balance. Now, since we scaled that to per 100, that tells us that this is our growth factor as a percentage. That's the main reason we did this. So that tells us our monthly rate is 0.5% because we scaled this to 100. Anytime you scale something to 100, you get a percentage. And that actually makes sense if you think about it, because an APR of 6%, if you divide that by 12, guess what you get? 0.5%. So that's scaling it to months. You could also say that that is prorating it to months. That word, I feel like that was somewhere in an important thing that's due today. All right. Give you about 15 more seconds. Let's clear our screen. Quiz time. I don't want that in green. That's silly. So this is due by 11:59 p.m. tomorrow in Canvas. What year was TCC founded? Hint, it's 1968. Remember, these are just to make sure you're watching the lectures. I'm not actually trying to make you do anything. This is just kind of, I don't want to call it role, but this is kind of a classroom participation thing. Remember, these quizzes are in Canvas. I just loaded that before the class went up. It will close tomorrow. All you got to do is type 1968. Do not spell it out. Do not transpose any of those numbers. That's the only answer that will be accepted. All right, so hopefully everyone's awake. Next up, we're going to go straight into the next worksheet, interpreting Y-intercepts as initial values. So we said that quite often we can interpret a Y-intercept as an initial value. Every line has two key characteristics: its steepness, which we called slope, and its location. Recall that the track phone example, when we added $20 as a monthly fee, it raised the graph up 20 units. So at that 0 minutes of talking, we had a height of 20. That was the initial value, or the fixed value. So we characterize the location of that line by specifying where its intercept lies, where it intercepts the y-axis, excuse me. In other words, the x-coordinate is 0. So that is a point with 0, 20. This is where things start getting into, they don't always have to make sense. I'm not saying that it's wrong. As a model, it can be completely right. It just might not make sense when you try and interpret the y-intercept. So if your input is time, then the x-coordinate is 0 has to be thought of as the initial value or starting point. But if you have a time series of data with inputs like 1990 and 1995, 0 is almost 2,000 years in the past. And when we talk about modeling things, usually the types of models we do are going to be inaccurate if you go that far in the past, especially if we're doing lines like we are in chapter 5. We haven't gotten to exponentials, so there's not going to be a lot of accuracy looking at 2,000 years worth of data. So when we're dealing with things scaled to their actual year, if you wanted 0 on that graph, when you look at its y-intercept, it is very often not going to make sense. Typically, the value is either way too low or way too high. Quite often, you'll get a negative value, and if we're talking population, how can you have negative people? What this does is it tells us if we want an intercept to make sense, maybe instead of using the actual year, we should use something like years since. Remember in this problem, we didn't talk about the growth in the Houston metro area as a year. So 0 was not the year 2000. I mean, it is the year 2000, but I didn't write 2000 here. And what that does for us is it gives us an accurate y-intercept. If I just wrote these as years, so this would be 2000, then 2002, then 2004, 2006, that means this graph starts at a value of 0, 2,000 units to the left of this thing, and this line is going to keep on trucking down. And it ends up being this big negative number. All right. So remember, you're supposed to be reading this stuff in advance in case we don't spend enough time with it here because we have so much to cover in class. Can I get this all in one? Let me zoom out a little. Hopefully we can still read that. All right, this worksheet asks you to interpret the y-intercepts. So we're not going to interpret the slope, we're interpreting the y-intercepts. Now remember, all these equation models are y equals mx plus b. So now we're looking for this number. That's the intercept. That's the initial or starting value that may or may not make sense in application. Okay, so interpret the y-intercept. I don't care what the slope is anymore. I don't care about this 0.05. I'm ignoring it. What I care about is the 20 and the fact that it's positive. So what that says is that the initial cost based on this model, if you talk 0 minutes, this should be the initial cost. So the cost is $20, why dollars? Because the output's in dollars, when 0 minutes are talked. This $20 counts as our initial fee. Or a fixed fee. Because no matter how much we talk, we're going to pay that $20 flat out. Now for this problem, it does make sense. Now remember, for this type of thing, just because it doesn't make sense doesn't make it wrong. It's still an accurate model. It just means maybe you don't want to go that far into the past. But this makes sense. For number 2, we're going to interpret the y-intercept. Oh, and by the way, this is the point right here for that example. 0, 20. That is a 0, not a 2. All right, for the concentration of pollutants, we saw this one before. This is the same equation, y equals negative 0.x plus 100. So the 0.8 was the slope, but we don't care about that at all. We only care about the intercept, which is the 100, and it's plus. So that says, doing this interpretation, assuming that it's accurate, assuming that it makes sense, that the concentration, that's the output, of our pollutant probably, is 100, then we got to have that in the appropriate units, parts per million, at day 0, when no days have passed. In other words, this is the time of the spill, assuming that we're starting the model at the time of the spill. Maybe we're not. Maybe the spill was a week ago, and this is just when someone actually came in and measured it. And that would make sense because we're going to have some concentration, and we can see that the number's dropping over time. Now, if this was, say, a negative value, it wouldn't make sense because you can't have negative pollutants. It would just be 0 pollutants. That's the least that it could be. So we're clearly not going too far back in the past with this model. Okay, so I got to clear my screen in 5, 4, 2, 1, boom. See if we can get 3 and 4 on the same page. I wonder if I can do that if I zoom back in. And no, I can't. Okay. So we're interpreting the Y-intercept, and now this is a unique one. This is unique because there's 2 of these. The top one is rounded. The bottom is accurate. So here's what Excel does. When you get this model in Excel, which we'll talk about how to build this shortly, when you go through and Excel gives you this number right here, this 5e to the 6th, that's just 5 million. Remember, that was 5 million. That is just visually rounding it because they don't want to throw too many numbers in this display. 5 million, I mean, that's pretty close to 4,700,000, et cetera, et cetera. But if you actually use the model, the number that is embedded is actually in here. It's just not seen. So interpret the y-intercept of the equation in real world terms. Note that we have 2 versions of the equation. Please interpret both numbers. So we're going to do it with both of them, but the actual number would, of course, be better. So what are we talking about? The Houston area population. Houston metro area. Pop was, let's use the accurate number first, and that's the 4.7 million number. And we're not going to say at year 0. We are not saying at year 0 like we did in the last 2 problems because of this right here. It says years since 2000. So the Houston metro area population, 0 years from 2000 is the year 2000. So that's the actual statement, the accurate statement. The other version, I'm just going to use ... dots for, because I'm running out of room. The Houston metro area population was approximately 5 million in the year 2000. So again, when we actually look at what Excel gives us, it's going to give us the 5 million. But the number that they are actually using is the 4,715,407. Now, I would say that this makes sense. Because 4.5 million people to 5 million people in the year 2000, that sounds pretty good for Houston. We may see a problem later, hint, wink, nudge, where we're talking about a population and it doesn't make sense because we don't use years since 2000, we just use the actual years. Okay. Number 4, interpreting the y-intercept, which is this number right here, and it's a negative, so be careful. So that's negative point, and then there's 10 of those zeros. We did this earlier. 3, 4, 5, 6, 7, 8, 9, 10, and then the 2. So that's what that number really is. Now, this number is absolutely tiny. This is absolutely tiny. The number this is ridiculously close to is 0. This is pretty much 0. So what that says is that the monthly interest, since that's the output, is, we don't want to say negative $0.00002 for a monthly balance of 0, because if the monthly balance is 0, the interest is 0. This is just from Excel calculating a whole bunch of data points, and it had a teeny tiny minuscule error, if you will. So we would much rather say, all right, we figured out that Excel just, that's 0. So the monthly interest is $0 for a monthly balance of $0. If you have $0, you're getting no interest. You're not going to get negative $0.0000002 in interest. Okay, let's clear our screen. Now, I mentioned earlier that I wanted to tell you how to be able to get this stuff right here. So let's pull up our notes. New share, notes. Oh, I was already on the notes. Or different notes. This R squared part, this is going to be important later. I just want to go ahead and mention it. But how do you add a trend line and an equation to data? You highlight your data and labels. So when you have in Excel, if you have your data already there, you highlight all the data. You want to highlight the labels too. So you're only going to be highlighting 2 columns of things along with their labels. And then you'll go up to Insert. And then you'll click Scatterplot, the thing that looks like dots. And that'll give you your dots. Then you'll go to Add Chart Element. You'll add a trend line and make it linear, then add chart element, trend line, more options. You'll click Display the equation and the R squared. So I've actually never used Excel on this computer. Scroll down that far. So let's see if we can follow that. Let's just make a quick one of these. Okay. Zoom in a little. So let's just say we had a year. Why am I on that one? And a population. And let's go years since 2000. So let's go 0, 1, 2, 3, 4, 5. And then let's say the population, we're just talking about some random city. Let's say it was 100,000. Then it was 110,000. Then it was 119,000. Then it was 128,000. Then it was 136,000. Then it was 42,000. So let's follow the instructions. Highlight your data and labels. Go to Insert, and then the scatter plot, the thing that looks like a bunch of dots. This is your scatter plot. If you hover over it long enough, it says Insert Scatter. It gives you some options. Don't do any of the funky ones. Do the top left one. Okay. Then we're going to go to Add. So that gives us just the data elements. Then we go to Add Chart Element, which is right here. If you're on the whole screen, and it's when you're still under Design, it'll be the top left option. So add chart element, then trend line, and linear because we're doing a linear approximation. And that's it. So there's the approximation. Excel has done an insane amount of calculations for us. You do not want to have to be taught how to do linear regression in here. That would take us a month just to teach it to you and get you built up to, enough to do problems on the fly. Fortunately, Excel can do it in a half a second. Now it's nice to be able to see the equation, and this line seems to go through the points pretty well, but it's not perfect. This one's a little high, this one's a little low. So next we go to add chart element, trend line, more options. So add chart element, trend line, more trend line options. I missed a word, you get the idea. And it pulls up this little side menu. And we want to click display equation and R squared. Now, we're not going to see the R squared a lot, but we'll talk about it later. So display equation is right here. And you can't see it for the moment, but it just popped up. And then I'll display the R squared. So let me pull this up now. So again, when I hit display equation, there's the equation. And when I hit display R squared, this is a measure of how accurate it is. You can move those if you like. The closer this is to 1, the more accurate it is, but we're going to worry about that in a later chapter. I just wanted you to go ahead and have the instructions on how to do this. Guess what? You'll have to do this in your homework. You'll have to do it for exponential as well. So when you add chart element, trend line, if it tells you to do an exponential, you'll click exponential instead of linear. So that's it. That's how we can get our equation. So this interprets the slope and the intercept. So that says, okay, at the year 2000, the population was about 101,286, and then it's changing at a rate of about 8,485 per year. If you look at the actual data, this says the population was 100,000. The intercept says it was 101,000 because this is a model using real life data. This isn't always 100% accurate, but it's pretty close, so it makes sense. Let's do this another way. So let me just kind of stuff that to the side. Let's do year and then population. So let's go with 2000, 2001, 2002, 2003, 2004, 2005. I'm just going to copy paste these population numbers because it's the same information. Now let's make a trend line out of that. So highlight the data in the labels, insert. I got something covering it up for me. Scatter chart. The simple looking one. Boom, population, but now we can see the actual years. I don't know why this started on 1999, but it doesn't matter. Then we can add chart element, insert a trend line, do the linear one. And these points, I mean, look how similar they look to each other. But look what happens when I go to build the equation. So add chart element, trend line, more options. So, sometimes an extra menu pops up and you have to try that again. I honestly can't tell you why that happens. It's usually when you do them back to back. Display equation, display the R squared. And close that. The R squared is the exact same thing. The slope is the exact same thing. But look at that, minus 2e to the 0.07. What this says is that equation is y equals, oops, button, (8485.7). So we see the same change per year, but now it's minus approximately, and with seven decimals moving right, so that's 2, and then 1, 2, 3, 4, 5, 6, 7. It says the population is negative 20 million at year 0. Say what? How is a population ever negative? That makes absolutely no sense. It's because we did not do a year since that this now has a garbage interpretation of the Y-intercept. However, For the years that we're looking at, all these points are accurate, and it'll be accurate for a little bit moving forward. It would be even accurate for maybe 5 or 10 years in the past. But eventually, this starts turning into a terrible model because we're looking at too wide of a range. And it says that there were negative 20 million people in year 0 in, where were we? What metro area were we in? It doesn't matter. This wasn't the same place. This is, let's say, Portsmouth, which makes no sense because it's actually growing. Portsmouth is stagnant. Let's go Pleasantville. We're in Pleasantville. So the population of Pleasantville was negative 20 million 2020 years ago. Nope. The smallest it ever could have been is 0. That makes no sense because we looked at too long of a time scale for a population model. And that's not the only time that things won't make sense for a Y-intercept. But again, there's nothing wrong with the model. You just shouldn't be looking 2,000 years in the past or 2,000 years forward. The accuracy of the model is the exact same because the R-squared is the same. And again, we'll talk about what that means later. Or not what it means, but how to interpret it. Okay. So random bit aside, let's take off annotate, and let's go to 5.3. What just happened? Linear equations. Note, the y-intercept of a proportional relationship, which means there is no initial or fixed amount, that means it's 0. If there is no initial amount, if there is no fixed amount, then the y-intercept is 0. And we generally aren't going to write that because we'd be writing y equals mx plus 0. Why do we ever write 0? No. You just write y equals mx. That's a proportion. The y-intercept of a proportional relationship has no initial or fixed amount. Its initial or fixed amount is 0. We are usually not dealing with proportional relationships moving forward anymore. The slope is proportional, which means it's just a multiplier with the x, but we very often have these initial or fixed amounts. So we're not saying that these equations are always proportional. They're only proportional if there is no intercept. So this is proportional. If the intercept is not 0, it is not proportional. We can say the slope is proportional, but not the whole thing. And that's because in order for something to be proportional, 0 and 1 has to relate to 0 in the other. If there's an initial value, 0 and 1 relates to 20 in the other, or 0 and 1 of the things relates to 100 in the other, or 0 and 1 relates to the 4,700,000 in the other. How are we on time? 10:20. So if you know the slope and you know any coordinate, you can plug in these 3 numbers to find the y-intercept. We talked about this before. If you have some coordinate, some x comma y, you plug that into the x and the y, and then if you have the slope, you plug it into the m, and that'll be able to give us our y-intercept. The larger the value of the m, the steeper the line. Slope can also be negative. We saw that with the concentration problem. If you're given an equation not in this form, solve it for y to put it in slope-intercept form. That's what slope-intercept form is. So a lot of this stuff we already talked about. It's just reiterating important aspects. A couple extra new words here. We use the word accumulation when things are increasing, which means there's a positive slope. And we use the word depreciation when there's a negative slope because they're decreasing. So like your home, typically over time, not necessarily from month to month or year to year, but typically over time will accumulate value because homes typically rise in value over the long term. So home values accumulate, but your car, if you've just got a standard car, if you're not driving around some fancy rare muscle car from the 60s or something like that, or something they've only made 100 of, car values depreciate because they break down, newer things are made that are fancier and have better technology, so the old stuff loses its value because nobody wants it anymore. So that car value would be depreciating over time because it has a negative slope over time. And then another reminder, slope is a rise over run. The denominator will tell you how far right to go, and the numerator will tell you how far up or down to go depending on the sign. Again, almost all of this is stuff that we have done before. I am just reminding us because some of this might come into play very, very shortly. Okay. There we go. Nope, wrong thing. There it is. I keep forgetting that this is in a Chrome file. So let's zoom back in. Here's a little preview of Excel population. I am likely going to be assigning this one. Remember, every single Excel has a preview in these files somewhere, so if you get stuck, it's usually a good idea to come to these. So here's a population model. These little data points show what happens to the population over time. And then they do use a line to approximate it. Here's the equation of that line, slope, intercept. And you can see that it's okay, but it's not great because it's not really predicting these accurately. It's not predicting these accurately. It's only super close in this range and this range. And the further you go out in time, the worse this is going to get because it's going to get steeper on the right and flatter on the left. And then they ask you to do a whole bunch of things. And then what they do is they say, okay, instead of looking at the specific years, they break it down into just looking at the years since 1950 and look at how much better that approximation is by looking at a shorter time frame where these data points are more accurate, you get a more accurate model. This is okay, but it's not that great. This is really good by narrowing our window of time. Okay, but that's nothing we're doing in here. 5.3, linear equations. We've seen these three equations before. C equals 0.05 m plus 20. You could rewrite that with y's and x's if you wanted, which is how Excel would probably write it. So y equals 0.05 x plus 20. Or this C equals 100 minus 0.8 d. That's the same thing as, well, they have those terms written in backwards order from how we would normally do things. So let me rewrite number 2. That's C equals negative 0.8 d plus 100. That's a d. This was the concentration problem where we had 100 pollutants initially in parts per million, and we were dropping by 0.8 a year. This was the other one where we had a 0.5% monthly interest when we figured that out ultimately. And again, all of these can just be rewritten with y's and x's. So you can use letters that are a little more appropriate, like cost, concentration, interest, base value, days since, minutes, or you can just flat out use x's and y's, which is typically what Excel is going to do, which is typically what you're going to see in your homeworks. No matter what, if it's solved for one of the variables, you're assuming that's the output variable, the y. The number in front of your input variable is the slope. The other number is the intercept. Oh my, those numbers are teeny. Okay, let me scroll in so we can see that. I'll have to highlight the numbers that we need, and then we'll come back to it. Use the values in this table to determine the linear equation in the form y equals mx plus b. So in other words, we need to determine the slope and the intercept. So we've got to determine the slope and the intercept between the 2 points for Palm Coast, Florida, where x is years and y is population. So the output, the y, is our population. The input will be years, not a year since, just a regular old year. And we're specifically talking about Palm Coast, Florida. So in this table, we got to find Palm Coast, Florida. Palm Coast, Florida. Most populous, not seeing it, not seeing it, not seeing it. Fastest growing, oh, here we go, Palm Coast, Florida. So let's pull up the annotate for a second. So this is the row we're looking at. I got some stuff in the way. Now, the first two columns are a population in 2000 and then in 2010. The next two columns are the change as a number and a percent. So as a number, that's the total change or absolute change. The percent would be the percent change. They did not ask us to do any of that. They asked us to find the model y equals mx plus b, which means we need to find the slope and the intercept. So we don't need any of these numbers at all. We're not going to use them. For Palm Coast, Florida, we're using these numbers right here as the outputs. And what were the inputs? They're up here. The years, 2000 and 2010. If you want to call these x1, x2, y1, and y2, the 2000 is the x1, the 2010 is the x2, because those are inputs, they have to be x's. The 49,000 number, that's the y1, the 95,000 number is the y2. So if you wanted them labeled as points, the first one would be 2000, 49,832. And then the second point would be 2010, 95,696. That's a pretty solid growth in 10 years. They've doubled their population in 10 years, and close your parentheses. And there's no in millions here. These are the actual numbers. That would be a very big city if it was 49 million. So these are the points that we're going to plug into our slope formula as a reminder, and you're supposed to have this memorized, y2 minus y1 over x2 minus x1. That's how we get the slope for y equals mx plus b, because our goal is y equals mx plus b. We got to find the m, and we got to find the b. And it's easiest to find the m first. Now, I do want to do my actual work where the problem is, so I'm going to have to clear this in a hot second. Just scroll down. Luckily, I have my numbers written to the side. Let me make sure they're right. Yes, okay. It's clear. Scroll, annotate. So again, those points were 2000, 49,832, and 2010, 95,696. So our slope, y2 minus y1, that's 95,696 minus 49,832, all divided by. Then the difference of the x's, the difference of the inputs, 2010. Make sure you go in the same order. Do not swap them. That is the most common mistake made. Somebody will do the second minus the first in the top, and then the first minus the second in the bottom. Well, the bottom is 10. The top is what, 45,864. And if you do that division, you end up with 4,586.4. That's our slope. That is one of the two numbers we needed to build our model. Now what we have to do is find B. We already found the M. We found that. So our remaining goal is to find B. And I had that in our notes earlier. I said, as long as we have a point that it goes through, along with the slope, you can plug in those three numbers to the X, the Y, and the M, and then algebraically solve for B. Now, you can use either point, but often one is easier. Quite honestly, between these 2 points, there isn't one that is easier. However, if one of these had an x coordinate of 0, in other words, if one of them was an initial value, that's going to be the easy one to use because you're going to be plugging a 0 into the x, which makes this whole thing go away, and you will immediately find the y. We will see that eventually. So for now, and let me switch colors so we can tell what we're doing. So finding the b, I'm going to use this point. I'm going to use the first one. I typically just use the first one. It's not mandated. So the 2,000 is the x value and the 49,000 is the y value. So we're plugging in those for the y and the x. So instead of writing y equals mx plus b, what this will become is the y value is the 49,832, then equals. Then the m, which we found earlier, was the 4586.4. How did I know what to plug in? Because that says m. This was the number for m. Just pay attention. Then the next thing is supposed to be the x. Well, the x coordinate was 2,000, so that's times 2,000. And then plus b, we don't know b, so we leave it alone. That's what we have to solve for. Well, we got a product, the 4586.4 times 2,000. That's going to give us, well, the left stays the same, 49832 equals, that product right there is going to be 9,172,800, then plus b. And now we're going to subtract that number on both sides because we're just doing algebra to solve for b. So we subtract, and that's a big number to subtract, 9,172,800. I didn't have to squish it that far over there. Minus 9,172,800. It's not lined up very well. Please don't worry about that. And then let me go over here. If you do that math, the 49832 minus the 9,172,800, that should give you negative, watch that sign, 9,122,968. That's equal to b. So the numbers that we need are this, that's what we plug into the b, and this, that's what we plug into the m, because now we found the b. So our model, our answer, is y equals, we write the number for m, which was the 4586.4, then the x, because this is the variable rate, this is how much it's changing every year, so it's increasing by 4,586 every year, and then plus the initial amount, the interpreted initial amount, but it's negative, so instead of writing a plus, I'm going to write a minus, and then 9 million, let me put commas in here for friendliness, 122,968, and that's it. So that's our model. A model is an equation in math land. Okay. So once again, how did we do all this? Because this is important. You have to be able to reconstruct this. We had to go to the table and find the points. The time, the year was the x values. The population was the y values. Then we're supposed to be making a y equals mx plus b, and this is typically how it's done. We find the m by plugging in the 2 points. Do your math, get the number. Then you'll plug in that slope as well as one of the original points. Technically, it does not matter which one you use, as long as it was one of the points used to find the slope. I typically do the first one, but it's easier if there's a 0 somewhere. There wasn't a 0 anywhere, so you could have used the 2010 and the 95696, and what's awesome is If you plug in the 2010 here instead of the 2000, and the 95,696 here instead of the 49,000, when you do your arithmetic, you will get exactly the same value for B. That's what's amazing, and that's what's awesome in the world of math. So that's our equation. Plug in the X and the Y, solve for B. The algebra is always the same. There we go. Interpret the slope and the intercept. So for the slope, let me go back to red. This is the thing that's changing. What is changing? The population. So the population of this town in Florida, I'm just going to write Palm Coast, is increasing by, I'll be more specific. I can still say changing, but I'm really making sure that you see that it's going up, is increasing by, and then you write the slope number, which was the 4,586.4. What are these changing by? These are people that it's increasing. So it's increasing by that many people, and then a per. And then this is where we say the units on the x-axis, the input, which would have been years. Not years since something, it's just years, because we used the actual years 2000 and 2010. Okay, that seems sensible. It's increasing by 4,500 every year. I don't see anything wrong with that. For the intercept, the initial value, that says that in the year 0, remember, intercepts always relate to the input being 0, input being time, or years in this case. So in the year 0, the population of Palm Coast, Florida is, or was, negative 9,122,968, which makes no dang sense. You can never have a negative population. The smallest it can ever be is 0. This again is emphasizing the fact that we don't want to use population models to look at 2,000 years worth of data in a linear fashion. We need exponential or logistical models to do that. We have not talked about those yet, so don't worry about it. We'll get there later. Oh man, we only have 5 minutes. We're going to need to do the next one next class. There's no way we can do 3 in 5 minutes, but I'll at least show you what we're going to do. And I wish I didn't have to clear the screen, but I will. Okay. For a problem, someone just asked, do you have to include when something makes no sense? For this quantitative analysis, this worksheet type problem, yes, you would need to make sure that you're saying this makes no sense. In my math lab, that's not really going to be an issue. In my math lab, we're mostly just filling in numbers and blanks. You might have 1 or 2 questions where there's a drag down menu for make sense or not make sense. But I've only ever seen that once out of the homework problems. So thank you for asking that. But again, the point of this class is to understand things in the real world to be able to interpret data. So when you're doing this stuff 2 years from now for your own reasons, you have an understanding, not just for the math test. All right, let's take off annotate. Let's scroll down. Let me back up just a little. So for question 3, what we'll start with next time is, use the values in the table to determine the line between the 2 points for Palm Coast, Florida, where X equals years, and they actually have a typo here, which is amazing. So I would like all of you to make sure you make a note of this. X is supposed to be years since 2000. If you just let X be years, this is literally the same thing as problem 1. So they goofed there. that was supposed to say X is the year since 2000. So I'll make that same correction. So what we're doing in problem 3 is narrowing our field of vision. We're only going to look at a small amount of time, which will make the model more accurate. And generally, when we look at a smaller amount of time, generally, that's when we can say that the Y-intercept will make sense. We probably won't get a negative population for the initial value this time. So that is where we left off. We are almost done with 5.3, but we did finish 5.2. I didn't type it at first. Let me go back. I gotta clear my screen. Take off annotate. Go back to the file from earlier. So we said that 5.1, where are you, is due on the 15th. 5.2 will be due, I don't want to give you too much on the 15th since that's Excel is due as well. Let's call it the 20th. We are going to have a backup of homeworks coming up. Once this project's in, once the midterm's done, everything's going back to being due 1 week later. So again, this is the one thing that changed. I will update that in my math lab within an hour. Besides that, please make sure that you get on your midterm. Midterm. It's time. You got till the 13th. I think that is more than enough time, more than fair. The midterm, if you go back to your syllabus, I almost don't want to answer that question, but I will. It's 20%. So have a good one. We will see you next time on the internet. I'll have these videos uploaded within an hour. Have a good weekend. We'll see you Monday. Good luck on your test.